Good evening, everyone. A very warm welcome to Webstack Academy's Masterclass webinar. So today we are hosting the third Masterclass webinar, and today's topic is going to be a very popular and well-known topic, that is scaling web services for Indian students. So before getting into that, let me explain you the structure of the webinar, like for the people who are here for the first time. So for the first 10 to 15 minutes, I will be engaging with you all, explaining you about Webstack Academy and also introducing you to our speaker, Mr. Venkata Ramana. And after that, I will be handing over the session to our speaker. So he will be engaging you all for another 1.5 hours. And then after he completes, I will be taking back the session and I will be conducting quizzes for you all. So these quizzes, it will be open for another one day, that is 24 hours. And also guys, please note that you can take up the quiz only if you enter a correct coupon code. This coupon code I will be providing to you all at the end of the session. So you subsequently you can take up the quiz by entering the correct coupon code. And also the winners of this quiz will be getting exciting goodies, and also your pictures will be published on our social media platforms. And also all the attendees of today's webinar will be getting participation certificates. So guys, these participation certificates and these goodies are mainly for motivating all of you, so that it doesn't become a discussion type of a session. We want it to be a little lightweight, fun, and also like at the same time intensive learning experience. So don't drop out, stay back in the session till the end. Our regular timings will be from 7 to 9 p.m. And so please don't drop out, stay back in the session. So once I hand over the session to our speaker, if you have any kind of questions or doubts relating to the topic while he is presenting, you don't need to wait. You can just type in your questions and your doubts in the chat box. I will be coming time to time in the middle, and I will be asking your questions to our speaker. So you can feel free to type in the questions in the chat box anytime you have a question, so you don't have to wait. Okay, so with that, let me get started by introducing you all to Webstack Academy. So people know, like for example, WSA, we have been in the edtech for almost 20 years. We have started our original concept of skilling and making engineers employable way back in the year 2004. So that is when Emergy had come in. So Emergy is still existing. We are about 150 members organization, primarily doing embedded systems and IoT based training programs for college students and also for working professionals. And we established ourselves very well in the embedded domain. And then around 2008 to 2009 timeline, we started diversifying, and that is the time, if you see, Java and Oracle or Sun Microsystems was acquired by Oracle, and it had become a certification based program. So that time we used to run some training programs for international students. So these international students were from South Korea. So for them we used to run some training programs. And so that is how our association with application based training started. And then we became an Oracle workforce development partner in the year 2013. Then as time progressed, full stack web development became more popular and prominent, and then all the companies started adapting the full stack kind of roles. So that is the time we came up with the idea of Webstack Academy. So though Emergy still remains as our parent company, we started WSA in the year 2017 to 18, and it ran quite well. We also trained good number of students, and we placed them in good companies. But then pandemic hit, and then we were not able to focus on that, so our entire focus shifted to embedded systems. And now we are coming back with our full-time courses. They are yet to be launched. Probably I will be talking about that in the end of the session. So in the meantime, we are also running free internship programs for engineering students. Our recent batch finished just a week back, and we'll also be starting our new batch shortly. So if anyone are interested, they can register for that. And then we are also running these masterclass webinars every month. So this is what we are doing as of now. And then, so at a high level, what problem are we solving? So the problem number one is employability. We are making engineers employable, especially the engineering students who come from tier 2 and tier 3 colleges. They need to be skilled and coached in order for them to be ready for an employment. And so that is the problem number one we will be solving. So the problem number two is the people who have already taken up the job and who are not happy in doing their job, like they have studied something but they are doing something. So we upskill them and give them the profile and help them to get into a job. So that is what we are doing as an organization now. And then coming back to why we are doing these masterclass webinars. So it is very easy to understand, guys. There are two M's: mentoring and motivating. So when we look around fresh engineers coming out of colleges, we see that there is a huge gap of mentoring and guiding them with respect to their careers. And many of the times they are confused, and they have misinformation about certain technologies or trends, because of which they end up taking a wrong decision. So what we are saying is that when you take up a wrong decision, you are not able to um, achieve the potential what an individual is having. So that is the inspiration for us to conduct these masterclass webinars, and bring in people from various companies who have the real and actual knowledge and deep knowledge about what they are doing, and of course passionate to share their knowledge with a broader audience. um, so the second M is motivation. So you all require the push and inspiration to start off. So that might not be like you might start up today or tomorrow, or might be 6 months down the lane, or maybe 1 year down the lane. So that you can achieve what you want. So this is the whole and sole purpose of hosting this webinar. Okay. So this is the purpose why we are hosting these webinars. So guys, this video will also be recorded, and also the slides and the presentation what our speaker will be presenting, that will also be available, and it will be reaching to all your inboxes, your email, and it will also be published on our website. You can go and check it out there, and it will also be published on our YouTube channels. You can also have a look there. So with that, let me introduce you to our speaker, Mr. Venkata Ramana. So guys, please join me in welcoming Mr. Venkata Ramana. So just give me 1 second. So I have made Venkata Ramana a presenter. Okay, so Mr. Venkata Ramana is the principal architect of Flipkart and a seasoned veteran in the technology industry with over 2 decades of experience, including distinguished roles at Huawei and as a contributor to Apache Carbon Data. Mr. Ramana brings a wealth of expertise to today's masterclass webinar. His insights into technology, innovation, and leadership promise to be invaluable. Let's extend a warm welcome to Mr. Ramana as we eagerly anticipate his enlightening discourse. So over to you, sir.
Just a second. I just want to check if you guys can hear me, can see me.
Yeah, we are able to.
Right, my voice is clear, right?
Yes.
Hey, hi everyone. I think it would have been good if it would be face-to-face communication and discussion, right? I think I'm happy to, address a mainly new guys, right, who has been into industry, who has been trying to learn, and then I think multiple webinars are done or presentations done for more for experienced people. So this presentation, I just kept it specifically for a new comers who wanted to from a college, right, who just understands or they would have tried it creating web service by themselves, right? But they wanted to know what it takes actually to make it productionized and what and use it in a industry, if really had to productionize and use it, what it takes to do it, right? So I kept the journey more in that terms than starting with tech first, more a method of keeping a purpose first. I think the way of presenting this. Um, so that's where that was my thought when I was actually preparing this presentation. Okay, maybe I think I'll just quickly, set the context for the presentation. One, why this topic? I think as a engineer, everybody would have built a smaller, big service, right? So you would have started creating a small service, which can be very minimal, very smaller service, and it works, right? But when it actually requires to work for what at India scale, right? Each of you will be working with some or other industry which actually works for India, right? That means the scale is too big. So there is journey associated with how, based on the scale, the architecture, the decisions change, right? And then I think I try to put that experience of or a journey, how a simple web service when really had to scale to the millions of requests, right, which have to handle India type of workloads, or the expectations, what it takes, right? So that is the overall thought process here. Just to introduce myself, I think I've been working with multiple companies, I think close to more than 20 years, right? My greatest strengths are actually designing a distributed systems and distributed analytical processing systems. This is my core strength. I think currently I'm from Flipkart. I'm principal architect who's handling the complete tech part of a data platform and data analytics and data engineering teams. So that means daily, I mean, I think petabytes of data at Flipkart, how to make them work for problems, right? The problems like fraud detection, problems like advertising, right? There are multiple problems with which data can be solving. So my space is more into data analytics and then data engineering. That is a course area where most of my time was previously spent on. I was also a open source contributor. That means, I mean, one of the Apache project committer, which is Apache Carbon Data, which actually solves the scale problem for the big data analytics. That is I'm also a committer there. So then I think my new interests have been recently, I think working on NLP on big data, right? This is, I think, quite a new space. How to make the analytics available for easily in different part of organization, including business, including different, different stakeholders within the organization, so that it becomes very simple to ask. You ask what you require, and then the analytics should happen, and then you should get back the response, and that is also should happen on a petabytes of data, right? So that is a scale plus the NLP is a challenge there. I'm currently would try, I think, working on the Gen AI space mainly from the big data analytics point of view. This is about me. So I think I will just come to the agenda here. So first thing is, like, let's understand what it scale means, right? For India, some numbers. That's what I want to put it, the expectations here. Then I want to, take two case studies. One case study of simple web service, right? Very easy read-only type of web service. What it means to scaling, right? And what technologies we can use to make it scale, right? For a problem like India, for a big huge scale. That's the first part I'll be serving. I'll be discussing, and then case two part, which is slightly the complexity increases because of slightly will take slightly more complex problem statement, like order placement in Flipkart or any other app you take from e-commerce point of view. In order places, there is some complexity associated with compared to the simple lookup. What it takes to design that, right? And what are the challenges and what are the decisions we can take, right? Um, in achieving that journey, right? That is the two typical case studies I wanted to cover on. And then end-to-end view of from the network, right, from a mobile, let us say, to the web service to scale, how end-to-end of overall, how do we plan it, right? How do we plan for the scalability of including network to make it work, right? That's the thought process. This is slightly different from a regular, trainings, which are like maybe I can say Kubernetes training or NoSQL systems training, which are more in terms of taking each of the area, just going into detail, understanding technology of it, and then understanding use cases, right? How actually it should be used. But this is slightly different in the terms saying first we understand the problem, and during that course of problem statement, we'll identify the technologies which will help us to make it work, right? So this will also open up thought process around why this technology is chosen, right? And you'll able to easily connect to the advantage and disadvantage of using these technologies, what it's solving, right? Then I think it's, now with information available on internet, you can just go ahead and then explore each of these areas to the level of detail you require. That can be details, you can go and do an offline job there, but what it should, at least I'm thinking that this should give you a thought process on why this is technology is used and how it is helping you. That becomes a key decision point in this overall journey. So, okay, let me start with the scale, right? I think everybody would have experienced, Flipkart or the Amazon or other e-commerce websites where there are sales happen, right? Just to give a number, on during the big billion day sales, right, of Flipkart, you can see around 1.5 billion visits happens, right? You imagine a curtain raiser event where at the mid of the night, or or the late in afternoon, whatever it is, time frame where actually the sale opens. So you assume that, I think, how many people, right, just opens at the time and wanted to start browsing it, and then, right, so it is not really a distribution of traffic uniformly of people of India across the duration of 4 5 days of sale. It's not really like that. There is a huge surge in the scale happens in that instance. And imagine that during that time, if website doesn't work, what it means, how much is the loss, how much is a trust problem, right? So it is important to deliver at that scale, and it's not easy problem, right? I think this is one of the biggest in the world, right? Because India is populous in the terms of China, right? So the scale is unprecedented, and the companies has to really make sure that it works. Is not a trivial problem, right? It is a huge problem. Delivering, making sure that it works at that scale, right? So a lot of engineering happens to actually make sure that it works, right? So that is one of the right. And then okay, let's say during that process, you have opened the app, you browse the corresponding product. Out of maybe 100 products to 20 10 products which you have browsed, you selected one and you purchased it, right? And during this delivery, right, during this big sale, the delivering packages, right, number of warehouses work to end to make sure that the delivery timelines are addressed, right, and taken care with so many people, systems, automations, robotics working end to end to make sure that it really makes it happen. Then all these things are also backed by web services layers, which will help in tracking those packages, ensuring that the right destinations they reach, right? And that means the fulfillment is done and not compromising on quality or the timelines, right? So imagine that during the time of deliveries, let us say the fulfillment service is not able to scale or it is down, then you can just imagine like all the packets or all the packages which are to be delivered are stuck in warehouses waiting for information to flow and then that tracking to happen, and then delivery happens, right? So 4 million packages delivered in 4 days is like from small to big, right? So it is not a small problem, and it is a problem of scale, which is, I think, every company in at least in India will be solving for. So that is just to give you a view of what is the scale for India means, right? Okay, let's take a specific problem now, right? Let's think of scaling. Let's take a simple example of, sorry, let's take a simple web service, right? A lookup type of web service, which is more a read-only type of service. What it means starting small and then scaling it, right? Let's understand a journey. So I just put a very simple problem statement here. Let's say you're opening your mobile and you're seeing a product, something, a refrigerator. You clicked on it and you're finding the details of the refrigerator, right? So as a college project, if you require, this has to be solved, right? Now it's very bright, so I mean it's very straightforward. You just create a web service and host it on a VM using any of your language, Python, Java, whichever the web service you wanted to build it, right? Create an API, create a mobile app, and like API call, let's think that is get product detail is the information. Then you render that information in the app and then make it work, right? So that might look so simple and straightforward when we actually take a problem statement for one request of like getting product detail. So now, okay, let's think we built it. I think most of you guys would have done something similar, I'm sure. Creating a very simple service, web service in one VM, one virtual machine, and then you can easily do 10 requests per second because you know the API endpoint, and then the mobile app will actually communicate with the corresponding get product detail HTTP end request, and then it serves, right? So it can easily scale backend the data. Okay, what is required for product details? You can just store it in MySQL database, and as you actually query 10 requests per second from the mobile app, the 10 requests per second goes for MySQL, right? This is very simplistic and way of solving the same problem. But what are the challenges here, right? As we wanted to scale, it can do some 10 requests per second. That is the limit, or it will tough to latencies increases after when we increase more number of requests per second, right? So now, okay, let's try start scaling it. You can see that I just added one more zero here. Okay, 100 requests per second I added, and then 10 VMs now, because each EM capability and then what are the MySQL request number of requests per second it can support are fixed for a given instance, for a given machine, and software combination. So now if I want to increase my scale, let us say 100 requests per second, if I had to do, then we'll think of some of the challenges there, right? What are the challenges? One, okay, you have one machine, the request is very straightforward. You have the IP of it, you just hit the web service and it will able to work, right? But if you have to serve for more VMs, then we have to add, like, web service is not really one VM there now. We have to distribute, let us say, into 10 VMs, right? And each VM handling a capacity of 10 requests per second. And then the web service actually is able to handle one, each VM able to handle more requests and then able to hit the MySQL layer. Now MySQL layer also, one machine might not work here. Now you're requiring slightly increase the complexity of MySQL system server, right? By adding, making multi-master or having more master slave replica. That means you have multiple nodes serving the same request, or divide the request across multiple nodes using some method, and then each of the node solves, actually handles more requests, right? So these are some ways to increase the number of nodes in the MySQL and then scaling it so that 100 requests per second is being able to get it. So what are the challenges which you got, which is addressed here? If you look at here, there are two parts which is given. One is request routing across VMs. So once we added the VMs, now the problems becomes slightly more complex, right? When a request comes, which VM I should send it to? Okay, let's think it's round robin. I get a request, I just select one of the VM and then publish it, right? So that means there is required a load balancer layer on top of it, which actually routes the request to the multiple VMs which are given. So once you started routing, now there are other problems of, right? What happens if one of the machine goes down, one of the VM goes down? How load balancer will know that, okay, now I should not, or I'm trying to send a request to the corresponding VM and VM not able to serve the request, right? So then 100 requests, if one,
Sir,
yeah,
we have a
sorry.
question from a student. So he's
Please go ahead.
asking, how do we route across multiple VMs? Is there any queuing process?
Yeah, so typically these are called load balancers. This, now the problem from the previous slide to the new slide, next slide, is we added a layer called load balancers. These load balancers are very popular in industry usage, right? Some of them are software based, some of them are hardware based, where they can really do multi-switching, right? Switching, multiplexing across that IP address. When a request comes, it can quickly do a request routing, and some of both software plus hardware combination, which will help to route the request, right? So that is those are called load balancers. And these load balancers, we give a set of IPs, let us say 1 to VM 1 to 10, right? All these 10 IPs I give it, then load balancer distributes the load across them round robinly, right? There can be different other policies on the load balancer, how to route the request. Uh, that can be further detailed, explored, but I think a typical round robin way of distribution is popularly used, right? So but here still where we stand here is we are serving the 100 requests per second type of right speed. Now the other part which I was saying is that let's say one VM went down, right? That means there should be a mechanism to circuit break saying that this VM is down, let me distribute to only to 9 VMs. That means when you distribute across 9 VMs, then again the load on each VM is increased. What happens if 3 VMs are down? Then the load on the each individual VMs have further increased, right? And then the latencies will shoot up. That means we have to have some protection on the VM, right? What happens if 9 VMs are down? Only one VM is there. Then that means one VM is given a traffic of 100 requests per second. Then it can't scale, right? Obviously, it will start, latencies will start hitting into minutes and all those things. So that means there should be a mechanism here to actually, that means they're alerting the, I mean the solution can be create alerts when then VMs goes down, and then some person can come and then switch on the VM, new VM, and do it, right? This still is possible, maybe 100 requests per second, not every VM, I mean only 10 VMs are there. I can have some notification mechanism, and then one person who can on call can support in bringing back the VMs with some automation scripts, right? In maybe in minutes, right? Before the bigger damage happens. So still the numbers, because VM10 is only 10 machines, such things can be done, right? And also in load balancer layer also I can give in load protection, saying that one VM maximum of 200% traffic I want to give, right? That means 10 into 20 requests per second. After that, don't overload that VM, just drop the packets. That means the users will start getting failure, saying that, let us say some of the VMs are down, and then already each VM's load maximum limit is reached, then load balancer will start sending a message back saying 5x failure, right? And then the app will show, okay, either the website is busy or it is a failure, please try after some type of experience, right? But still it is more controlled experience than if you don't have a load protection applied for each VM. Just 100 requests going to that VM, or that VM also will die, right? So that means at least I'm very clear saying, if you're having a load balancer and then load protection, at least guarantees that existing VMs are healthy and they're able to serve the traffic, and we have a very clear degraded scenario in a controlled way, right? I'm not saying that this is a solution, but the problem when it reaches to maybe 100 requests per second, this can be a probable solution where adding a VM and then load balancer on top of it will help, right? And same applicables to the next MySQL, because MySQL machines, when you have multi-master, that means multiple nodes, each serving a corresponding request is there, then they require a routing layer. There are MySQL routers and load balancers even can be applied here, who can actually route the request across multiple nodes in the MySQL cluster, across master slave or across multiple masters, so that the load is distributed across them and then you're able to solve the request, right? But there are some challenges in what I explained right side here. But still, okay, maybe at 100 requests per second, I can use this type of method to solve the problem. And when it comes to the, I think there are other parts is can be like, maybe there is a very repeated read-only type of data, images, common data, right, which is required, can be cached here every time, storing in MySQL or a file system and then getting back and serving using web service. It becomes overhead, right, as a number of requests, because that's more a refrigerator picture will not change very frequently. So it is once there, maybe if it will be same for a couple of days or more, or a couple of months. So why don't we cache it? And so that is one of the optimization which we can do. But in this current state, we are not done that optimization, right, in this slide. So then I think we covered. And similarly, when MySQL is down, same problems like we have seen in the VM. When something MySQL server goes down, then we should have a plan to route the traffic across multiple requests, and then load protection. All those problems has to be even solved in the MySQL routing layer, right? So, any questions still here? I think just before going to increasing the scale now further, I want to increase to 100,000, right? Into 100 more X, right? Then what problems we'll say we will go deeper. But any questions still here? You guys can
If you
shoot
have
questions, I
any
think.
questions, you can please type in the chat box.
Yeah, you guys keep I mean typing in your chat box. I mean, I think I will give some pauses in between, just wherever logical, right? You guys can, we can go to the problem and discuss on it, your questions. So now what happened here, right? We started increasing the scale, right? Now 100x more increases the scale. Then now let's try to increase the scale and see what happens to the same architecture, same design. Load balancer, okay, we'll add more nodes and it's able to load balance across multiple VMs, looks fine. Now the VM started become 1000 VMs. So 10 VMs versus 1000 VMs altogether different problem, right? That means suddenly some 10 VMs can go down, 20 VMs can go down. And managing them, previously as we told, we have on-call person who is actually sits and then bring back the VMs is not possible for thousands of VMs, right? We require some better service solution here. And to make it more predictable, it is not very straightforward for thousands of VMs, right? Interestingly, I think if you know the data center type of setup, right, where a probability of this going down will mainly problem in the most of the VMs we see is mainly disks, right? There are RAM and other CPU and other parts which of the machines which can also fail, but I think more very frequent, I think at least the point of failures are more general disks. They come with a very limited lifetime, right? I mean, you would have seen that, okay, maybe you would have got a USB drive, you kept all your photos in that, you stored it for 2-3 years, it is working fine, looks good, right? But each of them have a life cycle of how many reads and writes it can support, right? That means, let's say it can do maybe 1 lakh reads and writes. Afterwards, the life of the hard disk is gone, right? So there are number of reads and writes done for each of them are limited. And as we increase now number of VMs, right? Thousands of VMs, thousands of machines, you can think for a simplicity. All of them writing, reading, right? I mean, undoing at operations, the life will continue to decrease. And then every day there will be hundreds of VMs which can go down. And having somebody to sit and then fixing these VMs or automation to do it is not very straightforward, right? And then we still are not, we reached only, if you look at the scale here, still I reached only 10,000 requests per second, right? And I already hit the limit of, I mean, like 1000 VMs, and maintenance is like hell. And problem comes not only in the VM layer, next in the MySQL layer, right? MySQL is not designed, it is a transactional database, right? What is a transactional database? Is it like a relational system where there is a table foreign key, all right? And then when you update a primary key, then foreign key is also updated, um, and then their expectations among transactions, commit, and all those things comes into picture, where they're designed for transaction type of systems. And here, and they have a limit of distributed transaction is not easy, right? One machine transaction happening within that looks easy, but when you have 100 machines of MySQL, right, and then you get a request of a commit, you should make sure that the commit is consistent, it can multiple all the across the nodes. So it will not, basically transactional systems like these relational databases will not scale after a limit, right? It is easy to do vertical scaling, means like improving hardware, putting a new hardware, new RAM, and all those things is easy, but horizontal to scale it, you will start hitting the limits. So when you start hitting the limits, then okay, hundreds of nodes, maybe I will divide the MySQL clusters into multiple small clusters, and each cluster I can have a replication from one to other and make sure that it serves some of the part of traffic. We can do all those things, engineering around it, to distribute the workload, to protect it, but it is hundreds of nodes of MySQL is a problem, right? That means it is, they are not designed for such a scale to actually, and we started hitting the limits, right? So then they require more engineering solutions there to actually solve this problem. So as we hit the 10K request per second, so now these are the problems, right? So cannot scale horizontally. I think I already explained the problems when we started it, right? But we wanted to hit 1 million, right? So now next problem, right? So what is the solution here when we want to increase? That means VMs. These are the problems we discussed, thousands of VMs. Now just think of it becomes 1 million. That means again two more zeros added. Then the VMs becomes 1 lakh VMs. So 1 lakh VMs maintenance is like, you can just, it will not be, I mean, like possible to do a manual maintenance, ensure that things are working across all of them. That's where this type of model will not work. There are better way of solving these, and those are the better architectural choices coming into picture. One of them will go one by one. The major layers, two layers we are trying to solve, one from web service and other from the storage point of view. Once we take the web service, right, what is a proper possible solution here? There is, you guys would have heard of what is a KTS, right? Kubernetes. So the idea is to replace the web service model with thousands of VMs with a Kubernetes type of, replace these VMs with Kubernetes basically. That is the proposed solution here. Okay, how it solves, right? What it is basically, and why it is anything different from maintaining 1,000 VMs. What it is different Kubernetes brings in to scale and then handle these VMs, right? What it brings in. If you understand slightly this architecture, right, diagram, I'll just give a brief, right? There is a control plane. That means who has an understanding, who is like your on-call person, right? Who sits and understands how many VMs are running, how many are not running, how are they behaving. All those monitoring happens using a control plane of Kubernetes, who has a scheduler who can schedule the workloads across multiple machines, who can bring up the machines, who can bring down the machines, right? And then there's a, I think this layer has some configuration and other service information maintained, metrics, like each of the metric of the machine is being monitored and maintained by this control plane, right? And he is the one who actually, this is the layer which actually manages the multiple VMs. Now coming to the VMs, right? There are some problems with the VM also, right? You would have heard of what a container is, right? This, like, the key difference between a container and the VM is, you can think container is very light VM, right? Which is really packaged to do the specific required, like VM is general purpose still, right? That means you can still run a Ubuntu on top of it, and you can start running any application on top of it. In one case you might be running a database, other VM you might be running a web service or something else, right? So each VM is still a general purpose. So what is done from the container is, it is very minimally packed required packages only, right? So that you can keep it very minimal and deploy it onto a required VM. Finally, it might go in deploying into a VM only, right? Here, Docker, you can example, underlying Docker, you might use a VM or you might use a directly hardware, but it sits on top of it's, that means instead of managing a physical or VMs, which will use a general purpose ones, which takes a lot of time to bring up, bring down, and then control, monitor, you make small containers, and those containers are like very small VMs which is specifically done for that corresponding job, and bring them and monitor them, right? So that is the way the Kubernetes works. Instead of VMs are replaced generally with containers. Pod is a slightly higher abstraction to the container. That means I can keep related containers in one place. Like example, I want to run a web service, and I also want to do a auditing or logging of the corresponding what's happening in the web service. So I can create two containers inside a pod. One is a log container, other one is web service container. Pack them together and put into the pod and deploy it. So both of them are, well, always together, and then one pod generates the actually handles, and the other pods actually does the monitoring part of it. So that is a typical example. For simplicity, you can assume currently pod and container. Container is the, I think, one container per pod, you can assume it, so that the container becomes your new VM, right? Which is doing a web service. That is just to brief you what a container is. So now this Kubernetes layer control plane can effectively monitor these, right? So when it monitors, what it can do, right? What extra it can do. 1 second. This window is disturbing me. Let me move this
So
way.
we have got another question from
Yeah.
Gaurav Patni. He's asking, what if due to some reason the mobile network is down? Will the system work on server?
Mm. Yeah, I think that's a good question. I mean, let's pass this question to the last one. There's a network section part of the last part, right? Which will
Okay.
go into the network and then understand it. But here, what we're trying to solve is that a VM goes down, and it can possible that we in the VM network also can go down, right? That means there is a redundancy required in planning these. There are two types of planning. One is internet going down. Second is within the data center you connected one machine, two machine, three, and there is this network layer in between, and that layer going down, right? So each of them has to be solved. That means there is a redundancy built in each of them, like multiple, maybe each VMs are connected or each machines are connected with multiple network cards, not with one card, right? It can go down. And then each networks are separated so that not all the VMs are in single network. It will be in different networks. The VMs are distributed so that one network goes down, still only those VMs are impacted. Remaining VMs are not impacted, right? That type of redundancy planning generally happens. And if you look at this specifically Kubernetes gives control of everything to the control plane, so that you can control the placement, you can control the life of the VM, you can control the network. What network I can associate it with, right? With the corresponding VM. Everything is software based. You can control it on a containers, right? So that it gives a virtual um, I mean way of connecting these VMs and then handling it, right? So what it brings in, I will just brief here so that I think we'll, right? One is containerization we discussed. There are advantages with keeping a small containers very purpose built. Those are isolated and then it works for the purpose, right? Easy to deploy, maintain, and all those. So that is from containerization. Then scalability, because there is a control plane who actually brings up the node, right? Nobody is physically bringing up the VM. You're just bringing up the container. So because it's automatically brought in, so it scales well, right? You can just tell them in the using this interface of UI user interface or the Kubernetes control interface, saying that now make it 10 VMs to 100 VMs, right? Or 10 containers to 100 containers. Just Kubernetes can make sure that identify the machine, install the container on top of it, bring it up, connect to the network, make sure that application is work, right? Everything is taken care by the control plane. So easy to scale, and the scalability is handled within the Kubernetes. And then high availability, this is like what we discussed, multiple VM, one VM goes down, other VM, how to handle it. That is baked into the architecture of Kubernetes.
So, sir, there's one more question.
Yeah, please.
From what you said, does adding Kubernetes only help the developers and not customers? You said controlling, right?
So it simplifies how a customer will benefit, right? The customer should not be impacted by the problem happening within the backend network, right? That means it will help the developers, in turn helping the customers, right? Otherwise, developer cannot help himself, let us say, right? And the VMs are going down and he don't have a method to handle them effectively, then in turn you're impacting the customer, you're impacting the business. So though we're solving for the customer problem, the problem is in the scale of scaling the web service to a bigger numbers, and that brings in the developer challenges, and that Kubernetes is helping to simplify and then solve the developer problems, right? So now resource efficiency, right? So other problem is like the cost, right? Let us say you increase it, sale happens, let us say only 10 days in a year, let us say, right? But if you want to procure so much of hardware, like what we discussed, 10,000 VMs, like 1 lakh VMs, we wanted to procure and keep, and you always pay bill for it, is costly affair, right? Instead of that, Kubernetes supports on the need basis, bring up the VM, bring up the container, and start serving the traffic, and again bring down when immediately when don't require, so that that's released, hardware is released back, let's say in a cloud like GCP or Azure, or right, then it's released back, and then you're not billed for it. Some other customer can use that hardware. So the scalability also brings in resource efficiency, right? And also we kept our containers very minimal so that there is no extra process, extra wastage is not there, and it just runs to the purpose, right? So all this brings in resource efficiency. And next is the self-healing. There is somebody who is monitoring here, control plane. A machine goes down, he knows that he'll get a notification saying that, oh, this machine went down. It automatically brings up the machine, right? And make it and bring it back and add it to the same list of machines, right? So there is a self-healing, auto scaling built into this, right? Okay, I'll also tell what is auto scaling is. I think I not covered here. Let us say the load on the VMs can be always monitored, right? Let us say each VM can actually start serving 10 requests per second, right? That's what we discussed. Or each container can start serving 10 requests per second. What happens if traffic suddenly increases? Then the current VMs should be protected, and then we should also have the load, right? New load. So what this control plan does is it monitors, also can monitor with load balancer how much load is coming, right? And it can, okay, looks like each of the VMs are hitting already 80% of their limit, right? Let me add more VMs. So we'll say autoscaler of Kubernetes, I will configure saying by range of 0 to 1 lakh machines, let us say. So based on the load, based on the utilization, it can keep on add more and more number of machines and constantly monitor the utilization, and it can scale the cluster of containers dynamically, right? So that it can really scale to make sure that it works, right? That is one important property of what Kubernetes is solving it. And then portability, I think portability problem is more like, because this container is standardized, I can run on any VM, I can run on any hardware. One machine having 100 cores, one machine have 10 cores. My container is very small, so that I can run more number of containers on that, right? And because this container Docker is a very standard, it can work on private data center, it can work on public cloud, it can work on Azure, it can work on GCP anywhere, right? Or it can work even on your local laptop. So that way there is a portability of also is brought in because of containerization. And next part is DevOps enablement deployment spec. This is, I think, very crucial part where of the part of the way why the Kubernetes has been used for this, right? Here the difference between a general automation methods to bring up the corresponding VMs versus deployment spec of Kubernetes is that Kubernetes deployment spec, you give what the state you wanted the cluster to be, right? You just tell the state that I want 100 nodes, I want network like this, I want number of services like this, I want to give a load of 10 requests per second for each VM. All this what you want your cluster state to be, right? You just give the spec. It is duty of the control plane of to the cluster as much nearer to the state what you requested for. If a machine goes down, no, you are requested 100 machines. Let us say, oh, one machine went down. Let's add one machine and then bring it back to 100, right? So that way, you spec says what the cluster state required to be in, and then the control plane works to make sure that it meets the scale requirement demands. That means basically scale is bringing in all these challenges what I explained previously, right? And then Kubernetes is simplifying and solving those problems to make sure that such a scale, such a bigger workloads really work, right? Not just theoretical, right? To make it work, that is the advantage of what Kubernetes is bringing in. So this is the brief. That means that the solution here is to replace the VMs with Kubernetes and then scale it to the thousands of machines. VMs are lakhs of I mean, VM I'm using here for container also, right? Container 1 lakhs of containers I can scale, and then it can work. So till
So,
here,
sir, there's
any
another
questions?
question from Shubham Ranjan. In this architecture, can a worker be placed in different location?
Yeah. So this there is a location as explained, right? When actually data center, when you take the actual physical data centers, there are, I mean, like lakhs of machines, lakhs, I mean, and tens of hundreds of lakhs of cores, right? Machines are there. So those are typically distributed across. Again, there are, it is the complete data center will be divided into like zones, right? and each zone is again divided into fault domains, right? Basically, there is a breakdown happens where redundancy in the network, redundancy in the even building, right? Redundancy in the floors, redundancy in the electricity connections, redundancy into the cooling systems. Everything is baked into redundancy so that each there are small pockets of zones are being created, right? Or the fault domains are created, and then Kubernetes will have an we can the distribution of the VMs or the container. We can have those logics built into the control plane to really make them distribute across all of these different fault zones, so that something if supply goes down, only some of the percentage of the VMs goes down, but not all, right? And it can understand that now, okay, this has gone down, and I can bring up in one more fault zone, again more number of machines, or add one more machine in each of them, right? In the round robin. All these things can be done so that fault tolerance is achieved, and the distribution of the containers also is in control.
Sir, there's another question. I'm completely new to DevOps concepts. So what does Docker do?
Okay,
And is
see,
Kubernetes
mm,
equivalent to a load balancer?
okay, so I think load balancer is just a piece of software. It's like your router you have in house. You have your Wi-Fi router. When multiple devices, when it comes, right, and you request for it, I mean, while you're browsing website on one of website one on one of like google.com maybe, or amazon.com or flipkart.com, you're browsing on different mobiles, then your request again has to come back to your corresponding machine, right? Like the router which works to route across your devices within a house, and it connects to internet, and internet there are multiple other servers which are running, and you distribute the traffic and get it back, right? Similar job is the load balancer, right? The load balancer is just in between layer who is helping you to across VMs the traffic is being routed. So don't get confused, there's nothing else is there in the load balancer. That is a simple, right? It can be hardware plus, like router is also a hardware plus software. It can be similar, right? As number of VMs and traffic increases, your load balance becomes complex. That is a different part. You require a few servers to actually maintain the load balancers, but typically it is that router layer, right, which works. Now coming to DevOps. DevOps means when such a bigger from a software lines of code you write to make it work in production, we require to really have engineering methods, right? You require to have some scripts, compilation scripts. You might have to build scripts, deployment scripts, deploy in each of those VMs. And if everything, if a new fix you are done and you deployed in all the VMs, suddenly all the VMs, I mean that bug, you've done the wrong coding and everything, all the machines are suddenly down. That should not happen, right? That means you should be able to do some of planned or deployment method where first you do on one, verify that it is working, then you want to make it two, two to make it four, four to make it eight, right? Some method of deployment model so that you have controlled deployment happens, you have control and all the tests happens, right? So all these things comes under DevOps, okay, as a general term called DevOps, right? So basically Kubernetes also gives a spec based DevOps. That means you can really want tell like deployment model. Also you can say that what I explained, right? Increasing the number of deployment machines. That term used is canary deployment, one of the example. So Kubernetes understand canary deployment. So if I want a new software, new container to be deployed, it can make sure that not incremental deployment happens, and then it can take care, right? So that simplifies the dev operations. So that's the context I was explaining the DevOps. Okay, I think I'll just continue. Maybe we can again stop back for more further questions. If you look at the, so that's what, right, I'm explained here. Load balancer is there and then containers are there. Now how a container went down, how will the load balancer know, right? Or how will a control plane know that a container went down or it has ready to serve traffic, right? So in this diagram, you can see that there are some containers has in Kubernetes have something called probes, right? Probe is nothing but just a port on which if you ask a question, HTTP request saying that, hey, are you live? It says, yes, I'm alive, right? That is nothing but liveness product probe. And one more port on which if you ask saying that, hey, are you ready to serve the traffic? Yeah, I'm healthy to serve the traffic, right? That is nothing but readiness probe. What is startup probe? When a new container is brought up, initially it's not ready to serve the traffic, right? Then if a load balancer sends the traffic, then it will be rejected or it cannot be served. So when to start, right? That means there is a probe saying that have you started, are you started? Then after some time on the port, it says that yeah, I started now. I'm started and I'm ready to serve traffic, right? That is nothing but startup probes. So in Kubernetes, in the container lifecycle, right, bringing up the container and bringing down the containers, there is probes have been built into it, so that those are used by both from the load balancer to understand whether I have to route the traffic or not, and also understood used by the control plane of the Kubernetes, and to scale like example liveliness of the probe is been down. That means okay, this VM is down. Then automatically the control plane of autoscaler of Kubernetes will add one more container, right? And it will wait for start a probe to come back, and then it will start routing the traffic there. So basically, probes are mechanism to for both the control plane and the load balance to communicate the health of the containers, and can actually make the previous problem what I told, new VM going down or the container going down, to automatically to happen to solve this. This is a mechanism it actually uses. So that's, I think that's where I think the Kubernetes part I'm just coming out part, right? That means I replaced now a web service VMs with the Kubernetes, solving these, right, scale, and so that it can scale better. Now coming to the MySQL layer, right? What can be done there? What is the solution there, right? MySQL, I mentioned, it is a relational database, and it is the skill that it easily can hit the scale limit, right? And it's not easy to solve around it, because the primary is designed for a relational problem where transaction is very important. I can start a transaction, apply 3 tables, modify 3 tables, and then commit the transaction so that all the 3 tables are at one time updated. Somebody is reading it, should read it consistent state, right? These are the expectations with which MySQL type of systems, relational database have been developed, but it cannot scale after some limit, right? So then, because you really have to build 3 tables, and 3 tables data maybe in 3 machines, then somebody is there who coordinating, saying the first you update here, second update here, third update here, and then okay, once it happens, then only I will able to communicate back, right? So the relation systems, the scalability is limited, right? Then what is the solution here? That's where NoSQL databases come into picture. Okay, so the idea here is to replace the MySQL type of system with a NoSQL type of system. Okay, so how it helps, right? What is a NoSQL system? NoSQL system is, I think, very simpler in terms of you would have used a map, right, where you have one key and where you have a value. So NoSQL system is nothing but a key value store, right, where you just store a key and value. That means about relational, all those things, I don't want them. I just want, first of all, scale is important for me. Let us say there is a request comes, right, get product details. If I have product ID, I just want to give product ID and get my details. I'm not worrying about multiple tables, relational update, and all those things is a bonus for me. But what I wanted is a scale. So give me product ID on, and you give me that, and you get me the details, right? So that NoSQL systems takes out a SQL layer relation part, keep it very minimal, saying that you give a key, I will give you the value, right? The interface will be very simpler. Get a key and it gets the value. So what happens in that simplified method? That means there is a web service region, then so how then now key value lookup when it says, right? Now how to scale this, right, better? This is typically a HBase type of architecture, where I think maybe next slide will give more detail, where the key, what I explained, right? Like example, product ID. For simplicity, think that there are 100 products. So every machine, every region, you'll have one key range, saying that 0 to 15 key range, I will give responsibility to machine 1. And next 16 to 30 key range, I'll give responsibility to machine 2, right? Like that, I'll distribute the key range responsibility across multiple machines, so that when you ask for a product ID, get from product ID directly, the lookup can happen into the corresponding one, and can give you back the data. So basically, it is optimized for distributing the key space across multiple machines so that somebody who wants it directly can go and get it, right? That is what the advantage of NoSQL, taking out all the SQL part, just making that key value work, right? That is NoSQL databases. So these are very popular. What is advantages? What they bring in, right? Now key value store is one example, right? What it brings in. Second is the high scalability, because I just wanted to key lookup and I can keep the key in memory and start serving very fast, right? Or if I have a disk, I can organize using some indexes so that in a disk get the corresponding key value, store it, cache it in the memory, and give it back to the users. So basically, they're designed to just get that key, look it up, and get it back, so that they're very efficient in right in getting to it, in getting the required details. So that's why they are highly scalable. And key space distribution helps in distributing the responsibility across machines. Let us say now 10 machines are there. I want to add 100 machines. Distribute the key space again within 100 machines so that the responsibility is now distributed, saying that previously you are handling only 1 to 10 key range. Now you started handling only one key value number, key 1 to 2, 1 and 2 values only you handle it. 2 and 4 you give a responsibility to somebody else. Right? That means the key range can be broken further and can distribute the responsibility to multiple machines so that it can be effectively scaled. Right? That is nothing but NoSQL systems. So if you look at, it brings in very high scalability, and the responsibility also I can say, because 0 to, let us say 0 to 5 I given to one machine, I can give the same responsibility to 0 to 5 to other one and say that okay, if you are not able to, you are reach your limit, you hit the other one, right? So that way, even high availability, right, the responsibility wise, I can just give the responsibility and make it work, right? That way it can really scale also and also available, right? And efficiency wise, it's not doing anything else. It's not doing SQL parsing, it's not doing converting SQL string into a understanding it, lookup, nothing, right? The interface is just get key and value. So complete flow is been designed and for efficiency of it, so that there is no extra hardware, extra wastage of CPU cycles to do anything else, right? So what we are compromising on is the consistency, like relational, right? Two tables, one of table update and other table, both have a consistent view. That's what we are compromising. But then what it can allow is that one key update and one key fetching, because the responsibility is given to very specific node of it, right? You can actually get the corresponding key value. So that means a consistency of read and write. Somebody is writing, somebody is reading it, getting a consistent read from the what he has written can be done at row level. That means row is nothing but here a key value level. One key level, you can achieve that. That's what. So you have to keep that constraint that only row level consistency is available, and you have to design the system around it, right? And there is also in-memory caching is done in each of the responsible nodes so that the cache locality is there and you should be able to hit and get the result back. So this is about the NoSQL, right? That means we replaced the MySQL with the NoSQL, and because the responsibility can be easily changed using key space, they can scale better and they can be more predictable in giving the response, because there is nothing else is there, just getting a key and value. So what it brings in, so this is this key division, right? You would have heard a term called sharding, key sharding, partitioning, and all those. So this is nothing but a sharding. That means the method to distribute a key range across multiple machines is nothing but a term called key sharding, right? So it can bring in faster lookup, even faster update, because the update it just has to go and update the corresponding machine in which the actual value is there, right? So here they can actually support very high throughput, very high lookup speeds, and then they can scale better. So basically the new architecture now, what it look like. Okay, I'll come to CDN, but first, then the load balancer is there. Then now we become a Kubernetes instead of the previous one, and I can increase the containers to thousands. I can replace with NoSQL systems who can actually scale to thousands of nodes. So million requests per second when it comes, it can translate in thousands of containers looking looked up, and then millions of requests can be handled effectively using NoSQL systems. That became a million requests per second can be read from the mobile, right? Now other part, one which is called CDN, which is content delivery network. What it very still like image, refrigerated image is there, right? Image is a bigger, or a video is there, image is there. How when you browse in mobile very quickly, the information you should get it, right? What those information are generally saved using CDNs. That means those are stored very nearer to, not in data centers, right? They'll be there in maybe in Bangalore itself. If you take example, so many CDN, yeah, points, right, where information is stored, so that first it goes there, looks up and gets that images, and then remaining information clearly it goes to the web service and source, right? That means these are caches built into the network itself, so that this becomes faster for serving it, right? We'll have some, I think, CDN further details in the next slides, but the idea is here we introduce CDM for the static and image type of data, and then remaining are scaled using Kubernetes plus HBase as a model. So that is the first part, right? How we are able to scale a single service to using NoSQL and Kubernetes, and then making it scale for a million requests per second. How are we doing with respect to time?
So there's another question.
Mm-hmm.
So you are saying you have completely replaced relational database with NoSQL, or did you just add another layer above the relational database with which only helps with lookup?
Yeah, for a look, this specific service, right? This is mainly a lookup service, right? What our product detail is getting is a lookup service. So here we replaced the complete MySQL with because there is no need for a relational database here, and we can achieve similar, I mean, behavior using carefully using NoSQL, right? That means we replaced the complete relational part with NoSQL. Majority of the high throughput services does that. They don't use MySQL only for metadata and caching purpose. They get it some minimal information, but otherwise they don't rely on the MySQL type of systems. They always rely on NoSQL systems to actually survey both for update and then read purposes. Any other questions? I think before we go into this, I think this will take
Yeah,
maybe
so
10.
there's another question. How much time does it need to expand if there is 10 requests per second to 1 million requests per second? Will there be packet loss?
Yeah, so good question. Actually, there are in load balancers also support some retry type of constructs, right? Where there is also can wait for some time to if not there, then try with a different VM, right? That type of approach is also there. But when really a 10 to 1 million request scaling, I mean, is that is also dynamically is not really practically done, right? Because we know the sale days, so we'll scale it instead of 1 million request, we will scale it to maybe 50,000, 500K type of scale up. We do it, and then we rely on autoscaler, right? Because bringing up a corresponding node also has some time expectation, right? Because though the Docker we made it, Docker is very lightweight. It can bring it in, it can bring back, it can bring up in, let us say, 5 seconds, right? Or 10 seconds, it can bring up. But still, many of the cases, 10 seconds is not acceptable, right? Mainly from when it has to scale from 10 to 1 million requests, 10 requests to 1 million requests have to scale, even that is not acceptable. So that's where, I mean, it is like, it is incrementally added, machines are added, and if there is really a surge in the sale happens at midnight, or suddenly 10 becomes 1 million, generally such cases we pre-scale it or pre-warm it, so that they already are reached some 70% of the capacity, and then afterward they use for auto scaling, right? Right. So that is a balance generally done, but she still for non-sale days, we can, majority of the cases we can rely on a scale, right? Saying it should able to scale within seconds actually, because of the Docker. And one more point is like Kubernetes scales very well, like I was saying, within 10 seconds a new Docker can brought up, but databases are not like that, right? Databases, NoSQL layer scaling is not so dynamic. simplifies the scaling. It can scale better, but it is not auto scaled. Most of these NoSQL databases doesn't auto scale well. It requires pre-scaling, right? I mean, pre-scaling is nothing but configuration. You have to say that now you have to scale for 100 nodes, it will be able to scale, but it is not dynamic because there is a data locality, there is a caching which will help you to fastly serve the request, and all those things will be there. So it is generally scaled ahead. Uh, but MySQL systems cannot scale, but NoSQL systems can scale. That is the key difference.
Sir, there's one more question. What are some best practices for monitoring and maintaining the performance of NoSQL database at scale?
Yeah, so generally these, I mean, all these NoSQL systems, right? There is a monitoring layer. That means you will have lot of number of metrics, right? Per node metrics, health metrics, right? All of them are maintained, and then there is a alerting layer built on top of it, so that somebody a machine goes down, right? Or basically the latencies are shooting up, then if it shoots up to more than 70%, then your alerting will come, right? So there will be some manual work also will be required to be done for maintaining such huge clusters, but still with NoSQL systems, it is possible to be done, right? Each node level statistics also, right? Like example, till there yesterday the performance is good, but today the performance overall number of requests per second reduced. Then we have to go and understand the reason for it, right? That means we have to understand maybe um, because of an application change, now the data size, key value may values becomes too much big data has been started storing, right? Which has impacted the throughput. Or there is a network became slower because of some other application which has come started playing, and then the network is not able to serve, right? So that your though NoSQL is there, still the records, the network efficiency went down, right? So basically monitoring will be built in every layer, from hardware, VMs, NoSQL, each machines, then cluster level, then response level, right? All the levels there is monitoring built in, and alerting is being baked in generally in production systems to make sure that they can actually I mean solved. And they also all work with some buffer, saying that we will not be working all the CPUs with 100% workload and making the NoSQL work, right? We will generally load those each VM, NoSQL each machine with, let us say, 60%, 50% of the workload, right? And 50% we keep it open. I mean, we keep it um, empty, right, or not used, so that such things can be taken care, and then we'll have alerting on top of it. Any other questions? I think we're running short of time. I'll quickly move to this topic, right? It is a continuation to the previous one, but I think this is slightly adding one more dimension to the problem, right? So basically, previous one is more a lookup type of service. This is not just lookup, but there is some complexity of updating order is there, right? So this is an example system, right? What we want to build in the problem statement. I want to build an order service now. Previously, only product lookup is what we discussed, but let us say now I want to order a product, right? So what are the typical, I mean, when you're ordering, right, you'll place an order. That means, okay, order. Go to the order page and you say made a payment and then placed order, right? So there's one request of place order. Then you want to track the orders, right? Where is my order is, right? Whether it is ready to deliver, when I will get it, all the details. And then there will be delivery boy who actually wanted to take the trade, I mean, and then update the status of the order, right? That means while trying order, he will first it will go from one warehouse to other warehouse, then it will go from one place to other, and then it actually the product travels across, and then it happens till it goes to delivery to your home. So there will be multiple places where the delivery status, right, has to be checked and also has to be updated. Basically, in this overall problem statement, there is place order is like a write call, then track order is like a read call. I want to track it. Deliver order is like write call. And then if I put one service, I mean, let's say similar way as we start with simple, saying that one service I put it auto service, handle all of these requests, and then I started with MySQL, right? Then again, I think what we discussed, 10 requests per second, 1 VM, 10 requests, this is where we'll be stuck with. So just let's apply the previous understanding what we have built, right? And just directly jump in there. Okay, what I done now is that I added auto service, which is based on Kubernetes, and I replaced my MySQL here with NoSQL, right? Now what did the change happened? Because of which, and I added a load balancer layer here. Once I added this, now I can start serving number of requests or 1,000 requests. I can start placing the order, basically the write request, and 1,000 request order delivering, I can do it. And tracking now, because it is a lookup and read only, I can do millions of track requests per second. So I can run thousands of containers for serving the requests, and then I can have MySQL in which finally the writes and reads both will happen. Write will happen at thousands writes per second, but reads can happen at a million reads per second, right? So what happened with this is that sorry, we scaled each of these services effectively here. But the problem happened is because the writes and reads have a different expectations, right? Altogether, it might be different thing what you require to do. Then both will not, is kept under one single service and everything kept in Kubernetes. Then they will not again scale, right? Because that means hundreds of requests placed per request per second. If I want to make it 1 million, I can't make it. I mean, because it's the same service, then I have to increase number of 10 containers to maybe 100 more, 100x more, right? So basically to serve the lowest, which is right path, I end up in scaling all of them, right? And then still will not able to completely, right? There are other challenges along with not only scale here, right? So basically what happens is each is a different service here, actually different request here, right? Delivering order is different from placing order. So even the information to update and all those things will be different. The algorithm you write it to update it, all the things are different. So basically each request is different, but we kept it under one Kubernetes, one service. The problem of what happened is that because of which those each request have different service requirements, but I kept it under one, then I can't utilize the resources to the best. That means if a request of placing order comes, it goes to the same, it is being same container is being serving it. The other read request comes, or then it can serve better, but number of container requests are number of write requests are wasted, right? Because or it cannot be predictable because each request can be distributed across these uh, each of these corresponding container, right? So basically different services here in the problem statement have different resource requirements, right? But we kept it on one single service, which is challenging to scale again, because whether I will be underutilizing the resources to keep it free, or I will be overutilizing it, and then my latencies will suffer. Second is adding a new service stuff. Now if I want to add tomorrow a fraud detection service, I don't know how to do it. Right now I have to modify this service. Fraud detection might be completely different algorithm. It might require a cache lookup. It might do something else, which is completely different from this order, right? Then if I kept it in single service, then scaling all of them for different QPS requirements, individual QPS requirements becomes more and more tough, right? And because the latency of placing order will be high, right? Compared write request versus read request, or even fraud detection or advertisement serving, or different use cases will have different logic algorithm, and then write and read expectations, right? So though kept it in single service, it's tough to scale, right? That is a problem here. uh, and latency can be different, latency expectations can be different, each of them. Track order and place order have different scale requirements. That's what I mentioned. Right what's will have, and all operations are not all operations are synchronous. Okay, this is one important point from the service point of view, right? Let us say you placed an order. and there is a delivery person who is picking it and doing a fulfillment, right? This need not be together, right? That means when you are placing order, it is not expected that delivery person immediately gets it and then he operates it and then handles it, or it doesn't expect that the fraud detection happens and then you immediately because let's say fraud detection, what is fraud detection means, like example, if you place an order, there is somebody who is placing too many bad orders, right, in his history of doing it. So maybe then we should not serve him, right? Or we should come up with some more strict SLAs to serve him. Or a bad seller is there, how to catch a bad seller, right? These logics in general are complex. If you put this under the primary path, saying that during the placing order only I have to do all these, then my order request placing order latency will increase. Latency means the response time will becomes milliminutes, right? Which is not acceptable from mobile app point of view. Basically, the problem statement, not all of them are synchronous. Synchronous means happens in the same path, right? That means I can do some of them offline using asynchronous method, right? But here I kept it everything into single service, which is tough, right? So these are the typical challenges. So these come both scale plus functional challenges in this current architecture what we have put it here. So what is the solution here, right? Typically this is solved using event-based architecture design and queuing model, right? Basically synchronous and asynchronous separation of the services, and then queues and event driven design, right? This is a typical method of solving it. Let's understand the difference between this and this, right? Whether how some of the problems will be solved, right? First of all, to understand this diagram, okay, this is just now we made it order service, which is just placing order. If you look at the overall order here, delivery, and then all of them are track order is in single one here. But when it comes here, we just order placing is there with order service, right? It is nothing doing nothing else, right? And then it has come up with, this is same to the previous architecture, right? Like lookup or write type of operation where this complete service is tuned for making the order to work well, right? The resources have been, there's nothing else. It knows the one of the container how many requests of placing order it can do, right? You can easily benchmark saying that one container can do 100 requests or 100 place orders per second, right? I can easily benchmark, and there is no ambiguity there because it's only serves that traffic. We can easily scale that on the need basis and then start serving it, right? So place order. So that way this is now separated into single service where it just does that, and what are the principles we learned previously from Kubernetes and HBase can work now here, right? Now second part, what is the important from the event based design is there's something called queues have been introduced, right? Just to give a brief, what is a queue, right? Queue is nothing but, I mean, I think the database terms we have stacks and queues, right? It is just a queue from the database terms of queue is what we have meant here. The queue where we do the operation of ingestion first. Basically first ingested, you will get the first request, right? Who is reading it? So basically, there's a producer who is producing it and keeping in a queue, and who has the put first request will be read by the one of the consumers. Multiple consumers can be there. They can read the first request and then start serving it. So what it is bringing is this is bringing in asynchronous model, right? That means this job of placing order, once he updates the NoSQL and he also puts the request into the queue, then his job is done, right? He just replies back saying that my play order is placed. So there's nothing else is in this path which is happening. But reading from the queue is an offline process. That means there is a background processes which runs, who reads from this queue and then takes care of delivery person. It goes to fulfillment service. Fulfillment service is nothing but where the service moves, the packet moves from untracked across the different warehouses and those things, right, till the delivery. That is a different service. Now order is placed, asynchronously it goes to the service. This service now maintains its own database, NoSQL for what it required purpose, right? Now the database design also will be different from order service versus the fulfillment service, where here maybe warehouse will be there. Here there's no warehouse concept, let us say. Here warehouse ID, then there will be vehicles, shipments, right? There are different, all different funda will be there here. This database design will be completely different. But the information what flow here will be updated into this, and then these systems will work on top of that information and then make the delivery work, right? Now the advantage of this is that you can further split the fulfillment services into multiple more services, sub services. That is also possible, but for simplicity I put it here one, right? So where their delivery order, that means now this service is tuned for scalability, for tuned for NoSQL scalability, load balancers, all are tuned to make them really work predictably for the corresponding delivery, right? Fulfillment to be done. And then the track order, that means once the delivery state is updated, right, the state is again propagated back. Like example, the delivery state became it has moved from Hyderabad to Bangalore, right? Warehouse from Hyderabad to Bangalore. That information is propagated. How it has happened, maybe it would have, many things would have happened in this layer, but finally we moved from Hyderabad to, like, that information is propagated again into a queue as an event, and now the order tracking service actually reads this event and updates the database, so that when you ask for a track ID, order ID, it just looks at order ID, right, and basically as a key, and it can get you the in where which warehouse is the latest one, it is there, and then give back the information. So that way each service is tuned to do the specific job, and then the state information is being, event information is propagated from one service to other service, so that other service actually does take this information and updates the information like what the specific requires and gives the interface for serving it. So the main advantage of this also is the decoupling of the request, right? That means, like previous example what we discussed, if I want to add a fraud detection, then where to add a fraud detection is not very easy, right? Because order service, then it has called first fraud detection service, it has called fulfillment service, then tomorrow one more service comes, then my SLAs will start impacting, right? But in this architecture, what happens, I can add a new fraud detection service, and even fulfillment service will not know that there is a new service added, because this this queue can scale to one more consumer, and then it will start adding a fraud detection layer on top of it. But under fraud detection, that might have completely different database requirements. Though we learned now MySQL and then NoSQL, there are more type of databases like graph database, right, where it's like graph, it is stored as a nodes, the graph information, so that it can be looked up faster into it. So there are different other databases in which actually the way maybe the requirement might be there. So then each service can choose their own corresponding database to have based on the scale requirements, and the communication asynchronously happens and being updated, right? Similarly, advertisement service, tomorrow I want to bring in, then I want to advertise the related orders, which are order services made, then this request is being read here, and advertisement service will have its own logic of updating, uh, ordering the advertisements, ranking them better, so that what he has placed related orders, maybe it is meaningful, right? All of them can be done using this different service. So queues has made an asynchronous way of communicating across services and decoupled them, so that these type of flows are possible, and each of them can scale independently. Each of them have their own way of interfaces and SLAs, load balancers separated, so that they can scale better, and then the architecture is decoupled, right? Now there's also other part here, queue, right? Queue, like, I mean, I'm not going into detail of the queues here now, but here queue, like in a database which we have in Java or implement, there is queue dot something read, right? Information you can bring it, which is one machine capability, right? But in practical scenarios, these queues scaling is also a big important thing. Each queue itself, like in NoSQL database, you have seen that each key may is distributed on multiple machines, right? Similarly, this each queue itself are works on hundreds of machines, because if the throughput of is very huge, right? Let us say continuously, I mean, maybe I will take an example of this part, right? Continuously orders are like 200, I think hundreds or lakhs of delivery agents are doing their own work, and then lakhs of machine, I mean, trucks, and then warehouses, robots are working on it. So this huge much of data will be generated it will be in GBs per second, right? It's not really requests. We track their gigabytes of data, petabytes of data is generated every day, and these queues, it goes through these queues, right? And these queues are again distributed queues, different machines, and they can scale, right? You can assume something similar to architecture of HBase or the NoSQL database which you have seen, where each machine given responsibility and then can scale. Similarly, these queues like Apache Kafka is an example, right? These actually can scale literally to gigabytes of data and then can serve across these machines of multiple consumers, multiple producers parallelly, and then can happen, right? So, so I'll just summarize here what it brings in: independent scaling, each service can scale independently; low latency asynchronous processing, right? That means asynchronously the data will flow, and then each of them can actually reply back to the backend to the right asynchronously with low latency, not impacting adding new services on the latency on others. Highly throughput scalable queues, that's what we discussed. Then resource efficiency, because each of them does specific job, we can really tune the resources to make them best with placing the resources. Independent tech stack, explained like example, this can be in Java, this can be in Python, here it can be graph database, here it can be NoSQL database, right? Based on the need, I can choose different ones. So independent tech stacks are possible in this architecture. New service addition is easy. Then DevOps independence, right? DevOps again independence, because each service can have its own DevOps built. They can, I mean, I can upgrade this fault detection service, but I don't need to upgrade the order service. But previous, for example, if one container and all those things are there, logic is put, then that container has to be updated and all of them has to be updated, right? So that way there is independence given for each of the service, with even with respect to DevOps and maintenance point of view. So that brings in, I think, completes the use and event handling design point of view. Any questions here before we just try, I think, move to the network part? I will take 5 more minutes, I think, to close the network part, which is smaller topic, but I think please let me know any questions still here.
Guys, if you have any question, please write down at the chat box.
I mean, I just want even acknowledgement saying that you guys are able to relate and then think through, right? I think even that acknowledgement helps. That what I'm speaking, you're able to relate and then understand. Okay,
So there are no questions, so I think you can continue.
sure. I'll just move on to the last one, right? So now once I think we scale two services, next I think some of you are asking for, right, what a network means, right? I'm from a mobile, I'm taking a mobile and then I'm speaking, and then a data center PMs are sitting inside the data center and we are discussing about scaling of them. What happens if internet is down? What happens if how do we scale this network so that really able to get the low latency, right? So the scalability and latency even has to be solved from the overall network point of view. This is an example of Google data center, right? How a request comes here. If you take this, I think just to understand this, one is blue is the data center, green is the green or blue, whatever this color is the data center, right? And then there are something called edge point of presence, which are called POPs, right? And then there are edge nodes. So like you can think this is like maybe a data center which is sitting in Bangalore, or and then these edge POPs are there in throughout the India. Maybe every state has one POP, for example, right? And then next layer, this is there in every this edge nodes are there literally in every 100 kilometers, right? So that means maybe in one state there will be hundreds of edge nodes, or hundreds of thousands of edge nodes, maybe tens of, or yeah, less than 10 or tens of edge endpoints, and then one or more data centers, right? So that is the way the networks are distributed. So we can just see an example here, what it means of distributing these edge nodes, right? Typically, a user comes and then you like let us say place an order, then it goes to internet, right? So it goes to internet in public, different providers, and then it travels and all those things, and then it reaches a POP, right? Which is this point of presence, what I was saying, right? And from here to here, there are dedicated from these POP points to corresponding data center. There are very high bandwidth lanes, redundant lanes of network is physically laid so that these latencies are very low, and then this has a traffic priority which can take care and reach in a shortest path to corresponding data center, right? So this is the typical way of doing it. You can wonder where is this edge node or global cache is coming into picture. Like example, if you are typing something right in a mobile app, you will get the assistance immediately saying what are the related searches. You'll get it search, you will get it, you'll get related images faster and all those things. So those generally happens in between this, right? In this internet providers layer itself, right? There are edge nodes. These are the caches which are built in each of the space, who actually can serve directly the cache output from here to the end user back, right? So that means a user request will go to the internet and then the immediate and cache it can easily fast quickly solve, or it can continue to go to the pop endpoint and can reach the data center. So this way, the request what you are previously seen actually goes to that, right? And there are CDNs which are discussed. CDNs can be there at multiple levels, right? CDNs can be there in this pop layer. CDNs can be there in the internet service provider, where each service provider will finally, also will have a CDN network added to it, so that multiple service nodes of CDN exist and then caching happens here. So that way, the request which is coming to the user are served very quickly, and also routing happens effectively to reach the data center. So just this is the same representation of it with CDN into picture. Like just physically, there are, let's say you're in US server seats, then there are multiple users who are doing it, and it goes to CDN network, right? From CDN, first it looks up, if it's not there, then it finally will fall back to the corresponding POP, and then POP is not represented here, POP and then POP to data centers, right? So this is the way the traffic from mobile happens to scale and then work with high throughput. So each of these edge points also has limits on scalability, how much they can scale, and there is also routing happens across them, right, to make sure that the traffic actually effectively lands on host. And then after coming to landing onto your host server, that's where the previous discussion which we had with respect to scaling your load balancer, then load balancer, from load balancer, then you're scaling your Kubernetes, and then scaling your NoSQL or whatever the databases which are model will happen at this layer. That's all I have. Any questions? I think we can quickly take and conclude.
Yes, so they've asked, how can you consider the latency of async operations to zero?
There's nothing called zero, right? I think everything requires, it's all what it's like this, right? Yeah, let us say you are doing a placing order, you just want the order to be placed, nothing else, right? So what is minimum required to place the order, right? Maybe you have to update the status of order and put it into a queue or in NoSQL, right? That is minimal which is required, which will be in generally 5 to 10s of milliseconds, right? And that's what it will be, right? Anything on top of it you want to do fraud detection, you want to do advertising, anything on top of it, you just keep it out in asynchronous, and only the extra cost will be to put into the queue. Keeping a request in a queue typically happens in single digit milliseconds. That means irrespective of what you are doing in asynchronous way, on single digit milliseconds extra cost you put into the queue, then you are done, right? Then you can go back and reply back to the user saying that I'm done with my placing order. So that way, the I mean, it's not zero, but yeah, I mean, it is very minimal. And then because it's asynchronous in nature, more functionality adding will not change my latencies. Any other questions?
Mm, uh, no, sir. There's no questions. That's
Super. I think thank you guys. But I one more. You will be conducting any poll or just to I want feedback from the I think people who has joined, right? Whether they understood. Um, I mean, they were able to relate. Was it useful, right? To also do some poll there.
yes, sir. Just let.
Maybe you can do it offline also. That's fine. But that's thank you for I think guys for listening patiently for 1.5 hours on this topic. We were not able to hear you in case you're speaking.
Uh, now.
Yeah, now now we can hear.
Yeah, so as we conclude this webinar, I want to express our deepest gratitude to our esteemed speaker for sharing their expertise and insights with us. Your valuable contributions have enriched our knowledge and inspired all of us. So we appreciate your time and dedication, sir.
Welcome, guys.
Okay, so guys, this is our email ID and our phone number in case you want to be taking it down. And this is our Telegram channel. You can scan and join our Telegram channel. So there, sir, there's another question.
Yeah, please go ahead.
Doesn't Firebase replace all this process and make help applications without a need for backend? Why go through all this process? Please answer.
It is not exactly like that, right? I think there's no single solve for all because when the scale increases, the problem really has to be solved each area to effectively tune it and make sure that it works, right? So it is not one shot solve for all will fit for I mean for complex use cases. Each of them has to be independently and uh, scaled and then tuned to make the things work. That's where these architectural choices will be helping.
I hope it answered your doubts. So guys, these are our social media channels. You can scan and join in. Okay. So have you guys taken up all the links? So now I'll be sharing you today's quiz code. So please note it down. And the link will also be shared to your email IDs. You can take up the quiz there. Please note down the quiz code because you can't take up the quiz without it. So have you taken up the code? Can I get any response, guys, in the chat box? Without this code, you can't be taking up the quiz. So let me know if you've taken it up. And these are our scanners. I hope everyone has taken it down. You will be getting the quiz link in your emails. Okay, guys. So with that, thank you all for joining us today. To our attendees, thank you for your active participation and engagement. Let's carry forward the learnings from today and continue to strive for excellence. Until we meet again, goodbye, take care.